Today we're going to talk about work. So far, we've talked about work as a process of transferring energy into or out of a system. So, when we had an energy bar chart where something had gained energy, let's say that we lifted something up. If we lifted something up, we would say, okay, it gained gravitational energy. Maybe it's a box that we lift up, and we'll say the box and the earth gained gravitational energy. Where did that energy come from? We would say, oh, since those two don't match, we're going to say something put energy into our system. And we could say that that something was work. That work was done by a person in order to make the gravitational energy go up. So putting energy into a system makes the object gain energy. And then taking energy out of a system would be something like the brakes, right? Maybe we would have something moving and slid to a stop, and we would say, okay, all of this kinetic energy that we started with, all was lost. We know energy can't be created or destroyed, but the kinetic energy from the box got taken out of the box. Why? Because there was work done by friction, and that work done by friction was able to take energy out of the box. And so taking energy out of the system makes the system lose energy. It makes the object transfer its energy out of it to the surroundings. But when we're doing work, work can only be done by an external force, a force from something outside the system. So we can only say that work was done as long as the object doing the work is not included in our system. Work is done when an external force acts through a displacement. So you're going to get a new equation for work now. I think the best way to solve for work is to solve for your change in energy. This should be your number one way of trying to solve for work. But another way of solving for work is to say that work is equal to your force times your displacement. But you have to be careful. Those two lines in between there are really important. Those two lines in between there says that the force has to be parallel to your displacement. Only force parallel to your displacement causes a change in energy, and that's why it does work. So, work is positive if you are putting it into a system. So, positive work would make the object gain energy. This would be positive work. Positive work happens when your force and your displacement are in the same direction. So if you have a box and you're pulling the box and your displacement is to the right, really when we're labeling our displacement, we're going to label it from start to end. Here, this right here would be our displacement. So if the force that you're applying is in the same direction as the displacement, it's going to be a positive sign attached to your work. You'll take your force times that displacement, put a positive sign on it, because your work is making the object gain energy. This work done by the person would be making this box gain kinetic energy. Negative work happens when your force and your displacement are in opposite directions. You want to think of friction when you think of negative work. So again, you could be pulling this same block, but this time if we're talking about this green force of friction, your displacement is to the right, but your force is to the left. And so when you're trying to find the work done by that green force of friction, we would say that the work done by that green force of friction, they're still parallel to each other. This force and this displacement, we're still parallel, but they're in opposite directions, and so that's going to be negative work, that your force is negative times your displacement. And that is going to be energy leaving the system. So that work is going to be work done by friction that is taking energy out of the system. The interesting one here is what happens when the force and displacement are perpendicular to each other. So for instance, on this force diagram, of course we have a force of gravity down, but that force of gravity is going down, and our displacement is to the right. And so the work done by gravity, you would think you would just multiply them together, but it's actually zero because they're not parallel to each other. Gravity is not making this object gain or lose energy. Therefore, gravity is not doing work on it. Same thing's true about the normal force. The normal force is acting on the object as it moves to the right. But again, the normal force is up and the displacement is to the right. And since those are perpendicular to each other, the work done by the normal force is zero. It's not making the object speed up, slow down, change its energy, and therefore it's not doing any work. So a few examples of work would be when something is being pushed to the right and the displacement is to the right. Our force and our displacement are the same way. We have work and that work is positive. But if the normal force is acting up on us while we are moving to the right, our force and our displacement are perpendicular to each other, so there is no work being done. But if we apply an upward lifting force to the groceries through an upward displacement, then yes, that's positive work. Those groceries will be gaining energy as a result. But when we carry our upward lifting force through a rightward displacement, that's actually no work that's being done. We're not causing them to speed up, slow down, or change their energy, so they're not doing any work. The other thing to say is that even if you push on something really hard, if the displacement is equal to zero, then the work you do will be equal to zero. And whenever your force is perpendicular to the motion, that's another time that you're not doing any work. For these diagrams, A, B, C, it says that the force is to the right and the distance is 5 meters horizontally. So we've got a distance to the right and a force to the right. There's going to be positive work done. This one says an upward force is applied to lift an object to a height of 5 meters at a constant speed. So it's an upward force, an upward displacement. That's going to be positive work as well. This one's a little weird because we're going to the right, but our force is at an angle. There is work being done here, but we would have to find the component, Fx. We would say that it's the Fx times the displacement. That would be equal to the work that we did. When we're talking about work, you are going to start thinking of work only as force times distance and trying to answer a question about a car starting at the bottom of the hill, taking all these different paths. Which one would be the most work? You can always think of yourself trying to climb up this mountain. Which would take the most work for you? Work equals force times distance is not always the way you want to think of it. Your number one way of thinking about work should be that work causes and is equal to your change in energy. Every single one of these cars starts on the ground at a height of 0, and every single one of these cars is going to get up to point D, and so they're all going to gain gravitational energy. And in fact, all of them will do the same work. The work done from path A is equal to the work done from path B is equal to the work done from path C because it was the same change in energy for each one. And it's going to be equal to the gravitational energy that that car gained. Oops, I keep writing UG. I'm sorry, you guys. That gravitational energy, EG, that the car gained. Okay. Again, when we go up the stairs or when we go up a ramp, you might have noticed that some stairs you have to climb up really steep, and sometimes there's like a long ramp as well. And the idea is this, that even when you, let's talk about taking the stairs versus taking a ramp. As long as you start on the ground and you end at that same height, you're going to do the same amount of work either way, that the work that you do is equal to that energy that you gained. So why do we have these really long ramps? Why don't we just jump straight up to the top of the stairs? There we go. Climb up a vertical ladder. What's the point of stairs? What's the point of ramps? If you have to do the same amount of work either way, because you have the same change in gravitational energy for each path, that means that you have the same work done for each path. The idea is that work is equal to your force times your displacement as long as they're parallel to each other. This first path going up the ladder, here's your upwards displacement, and you'll need an upwards force in order to get up there. For the second path, here's your second displacement. You'll need a sideways force to get up there. And for your third path, here's a much longer displacement, and I'll need a sideways force to get up there as well. The answer is, for the same amount of work done either way, that work can be given to you through a big force and a small displacement, like path number 1, or it could be given to you through a big displacement but less force by path number 3. And so this should remind you of impulse: big force, small time, big time, small force. But this time we're talking about work and our change in energy. If we're going to gain the same amount of gravitational energy either way, we could either apply a big force to lift something up a small distance, or it will require less force, but you have to go a longer distance. Mr. Carnduff likes to talk about this like when you're moving. If you're trying to lift a big, heavy refrigerator up onto the bed of a moving truck, so here's the wheels and here's the moving truck, and you want to lift it up. If you just had to lift it straight up a small distance, it would require a lot of force. You would have to say, okay, I have this small distance to lift it up, but I have to give it a really big force in order to make it gain its gravitational energy. But for that same situation, what you could do is put out the ramp for the moving truck. If you put out the ramp for the moving truck, you're making it be a much greater distance that this refrigerator has to go up. But now, when you're pushing this refrigerator, you only have to apply a small force. Either way, the refrigerator is going to gain the same amount of gravitational energy, equal to mgh. H is just still the same value. It has to go up that same height. But the issue is that in order to make it gain the same gravitational energy, we're going to say, again, that the gravitational energy gained by the refrigerator is equal to the work that you had to do. We don't care how you did your work. The work done by the person could have been a big force times a small distance, could have been a small force times a big distance. Either way, the refrigerator has to gain that same gravitational energy as a result. And so that is a everyday application of why you use ramps, and why climbing up the stairs takes a little bit more force than it does to go up a ramp. And so this idea that the energy gain is the same, but you can kind of spend that energy through your force and your distance kind of opposing each other that way. One last everyday example of energy would be a car. When you're driving in your car and you are going to hit your brakes and come to a stop, we could say that the kinetic energy that your car had is all lost as a result of the brakes. And now we won't really say it's lost. We're going to say that that's equal to the work done by the brakes. And so again, you could stop your car with a small force as long as you have a big stopping distance, or you could stop your car with a big force through a short stopping distance. The goal is to give yourself a longer stopping distance in order to stop. The other thing to mention is because the work done by the brakes is equal to your change in kinetic energy. You have to lose all of that kinetic energy when you're stopping your car. And so while you're losing all of that kinetic energy while you're stopping your car, we're going to say that the work done by your brakes is equal to your 1/2 mv squared, or the force from the brakes times your stopping distance has to equal 1/2 mv squared. What that means is when you're going faster, your brakes can't push any harder, but you have to have a bigger stopping distance. I think in driver's ed they even teach you this idea that if you are going twice as fast, it doesn't make your stopping distance be twice as much. Instead, when you're going twice as fast, because the speed is squared, your stopping distance has to be 4 times as much for your car. So if you're going 50 miles an hour down a 25-mile-an-hour street, you have to take 4 times the distance in order to stop your car as you would if you were traveling at the correct speed. And that's why it's not safe for you to speed down streets with little kids in them, is that they run out in front of you, you're not going to have enough distance to stop. So drive safe, go slow, practice your physics, have a wonderful day.